And my name is Jinsong Wu, and I'm now a professor at this Wuhan University of Technology. So here's my outline of my talks. Uh, First of all, I will give a big introduction, who's Wu, who's me. And then I will talk about the lithium of cobalt oxide, studied by the in-situ TM. And then I will talk about the intermediate and metastable phases during the solution of MOS2, the molybdenum, and then the metastable defects in the AMO isolation. I got my PhD from Beijing Laboratory of Electron Microscopy, and my supervisor is Professor Guo, and he's the leader of the TM community of at the time. And in Beijing, that the research that we did in Beijing Laboratory of Electron Microscopy is we studied the gallium manganese quasicrystal and its crystalline phases. So by using the electron diffraction, we found the quasicrystal in a new alloy system, which is gallium manganese. And then we also applied the high resolution electron microscopy to identify its atomic structure of the quasicrystal. And as you can see, the stacking of the structure unit is not periodic. So meaning it's demonstrating that it has a crystal, that quasicrystal structure. And then after I got my PhD, I moved to the France, the Académie de France in Nancy, France. And at the time that I studied the scratch-induced microstructure in quasicrystal, and we found some precipitate with a cubic structure. And my host professor is Professor Jean-Marie Dubois. And after that, I moved to Germany and I worked with Professor Knut Urban in a Jülich, the science center in Jülich. And in Jülich, I have chance to use the first aberration corrected TEM that installed in worldwide. So because of the aberration correction, the resolution of the TEM can be greatly improved. So say here, it can be improved from the 0.24 nanometer to 0.13 nanometer. And here is the corrector at the time installed. And then at that time, we studied the interface structure of the oxide, and many defects can be identified at the time. And so after that, I moved to the Arizona State University, and I worked with Professor John Spence for almost 6 years. And at the time that we start to formalize everything happened inside the TM. So we can come up with the equations and the simulations, and we also did a lot of quantitative analysis of electron diffraction. And sadly, about a few weeks ago, that Professor John Spence, he passed away at the age of 75. So it's really a great. After that, in 2007, I worked at Northwestern University in the USA, and I have worked there for almost 10 years. And you see that Northwestern has a very beautiful campus. And far south, we can say here's at downtown Chicago, and my colleagues at Northwestern University. They are wonderful, and I miss them. And then about 3 years ago, I moved back to Wuhan University of Technology, and I'm now running the Nanostructured Research Center. And here are the major instruments that we have in the center. We have a double corrected TEM, and we have a Talos, which is also a field emission TEM. And we have focusing beams that we use to do this simple preparation. And now let's get to a little bit background on the batteries, and then we'll get to the dissociation of carbon oxide. And say here, this current is that lithium batteries has become very important materials in energy storage. And in a typical lithium battery, it has three components or three parts. It has an anode, it has electrolyte, and it has cathode. And as we know that during charge, once we charge a battery, the ions, the lithium ions, will intercalated into the anode through the electrolyte. At the same time, the electron will also move to the anode through the Y. And during the discharge, because of the difference in the chemical potentials, the ions, the lithium ions, will move from the anode back to cathode through electrolyte. And because of this, the electron will be driven, also moving from anode to the cathode. So as you can see, that during charge, both the ions and electrons will be intercalated into anode. On the other hand, during discharge, both ions and electrons will be intercalated back to the cathode. And there will be a lot of electrochemical reaction happened, and also a lot of products due to the reactions. Sorry. Okay, so by using the TM, but how can we observe such electrochemical reactions at high resolution by TM? Because basically TM has a column which is always in very high vacuum. So what we can do is, as demonstrated by Huang, both Huang in people can use the liquid, the ionic liquid electrolyte to build a miniature battery inside the TM. And then the dissociation or under-dissociation process can be observed at a very high resolution. So this is an approach that we adopt. This is a holder tip that we used in our TM, the transmission electron microscope. And as you can see here, we have a golden rod, the sample, the electrode, the materials that we tested is loaded on this side, which is a golden rod. And say the electrolyte materials like silicon, like oxide, can be loaded on this side. On the other side, there is a tungsten tip. And then on the top of the tungsten tip, by scratching, lithium, metal lithium covered with lithium oxide can be loaded on the tungsten. And then the tungsten wire is driven by a piezo stage. So the tungsten wire, this wire can do very fine movement inside the TM. And by doing so, we can build a miniature battery inside the TM column. And then we can apply either a positive or a negative potential so that we can initialize either dissociation or dissociation and observe them inside the TM with high resolution. So in order to demonstrate that we have lithium oxide as a solid electrolyte, we can identify the lithium oxide layer by using EOS. EOS is electron energy loss spectroscopy. And by using EOS, we can distinguish lithium oxide from metal lithium. And by doing the EOS mapping, And it is clear there is a thin layer of lithium oxide at the interface between the metal lithium and the silicon, which is electron materials we use. So demonstrating that the lithium oxide is formed and it can be used as a solid electrolyte. All right, so the first story or the first result that I want to show you is distillation of cobalt-304 oxide. And here's a sample that we prepared. We prepared very fine, very small cobalt-304 nanocubes. The average length of these nanocubes is about 5 nanometers. And we grew those small nanocubes on top of fuel layer graphene. And you see here's the fuel layer graphene. And it decorated with a lot of nanocubes. And this is the first sample that we used. And the second sample that we use is the nanocubes. We can also load them onto the common fuel layer common nanotubes. And you see here's a small view and here's a larger view of the oxide cubes on the surface on top of the fuel layer common nanotube. And here's index mapping. And it shows that we have good sample for our test. This video shows how we can. Some problems. This video shows how we can assemble a miniature battery inside the TM column. You see here's a tungsten tip loaded with lithium, covered with lithium oxide, and here's common nanotube, and then here, once we make a contact, and then a miniature battery is built inside the TM column. And after that, we can do the dissociation. So here, this video, it shows once we make a contact, and you see the reaction front moved quickly toward this side. And here's this video shows the products of the reaction, and especially by using the high resolution electron microscopy, we can identify that the small particles is metal, is cobalt metal embedded inside the lithium oxide matrix. And it thus can be determined that this is a so-called conversion reaction, the cobalt oxide reacted with lithium, and the reaction products lithium oxide and cobalt metal. And then we can also reverse the reaction, and then reverse the BIOS. And then you see here, we can see clearly the formation of particles with very high contrast. And by using both the electron diffraction and the index mapping, it can be identified that those small particles are cobalt oxide. So this is a so-called deconversion reaction. And so by using also the diffractions, we can identify the dissociation products is the lithium oxide, and we have a highly diffused scattering ring, and this one is due to the cobalt nanoparticles, the small metal cobalt nanoparticles. And similarly, when we do the de-dissociation, and by looking at the evolution of the electron diffractions, and it is identified as the final products of the deconvolution reaction is cobalt oxide, as shown here. So here the lithium oxide, as outlined like blue arrows, is gradually disappeared, and then eventually what we have is cobalt oxide. And if we look at these reactions at a little bit higher magnification, and you can see the expansion of the fuel layer graphene as a substrate. And also you can see this cobalt oxide cubes become smaller powders. And if we look at this result at higher resolution and then more details, in the reaction can be found out. For example, there is an intercalation stage, and there might be a morphosization stage before the convolution reaction. And we did the similar observation on the sample, the small nanoparticles loaded on the carbon nanotube. And then here, because we have no substrate here, so the reaction can be observed at very high resolution. I mean the atomic resolution. And you see here's the cobalt oxide nanoparticles, and it has a cubic form. And here's a 110 lattice plane. And when the lithium comes in, when we did the lithiation, and you can see the nanoparticle is gradually become larger. And then gradually we start to see a very strong contrast of 311 lattice plane. And here's 111 lattice plane. And then a little later, if you can look carefully, then we start to see the 111 lattice plane, which is expanding, and eventually it becomes particles, the metal particles, which we can identify as cobalt metal particles embedded inside, say here, the lithium oxide. So if we can observe the lithiation, the reactions at very high resolution, and then we can get more information out of it. And these are the snapshots that taken from the video. And then by using the DFT calculation, we can gradually calculate the structures by minimizing the energy. And then based on the structure model, we can do the image simulation, and then we can compare the simulated images to the experimental ones. And then we have very detailed information about the lithiation, especially about the intermediate structures, or we call it the metastable intermediate structures before the conversion reaction. So here's the first story. And the second one is I want to show you is the intermediate and metastable structures that we found during the MOS2, the molybdenum dissociation. And this time we use, instead of using the diffraction, instead of imaging, we use electron diffraction. We use a so-called in-situ electron diffraction to observe, to investigate the dissociation process. And here's the sample, we look at it, but what we did is we recorded the electron diffraction. And the advantage of using selected area electron diffraction is we can truly reduce the dose. And once the electron dose can be reduced, then the artifacts due to the electron irradiation damage can be minimized. And so what we can observe is, first of all, we have MOS2, and gradually, and then we have a lot of superlattice. See here, we have extra diffraction spots appear here. And then gradually we have, again, a highly diffuse rain and a lot of rain patterns. If we look at this is the lithiation process, sodiation process. So instead of using lithium, we use sodium. And then if we look carefully at each experiment diffraction pattern, and then by using also the DFT simulation and the image simulation, what we can find is from the pristine MOS2 structure, if we have about 0.125 sodium intercalated, the sodium ions, they are intercalated every 2 layers to form an intercalated structure. But once once we have more sodium intercalated into the structure, and then it will trigger movement of the moly. So now there is a phase transformation from 2H to 1T phase. And this is when we start to observe a lot of extra diffraction spots, or we call the superlattice spots inside the SAED pattern. And once we have more and more sodium integrated into the structure, and then the conversion reaction will be triggered, will be caused. And then the final reaction product is fine moly metal nanoparticles, and also with the sodium sulfur. So, and the each intermediate structure is first defined by the DFT simulation by minimizing the energy. And then based on that, we can then do the electron diffraction simulation and compare the simulation to the experiment ones by measuring the d-spacing and the angles between the spacing carefully. All right, so here's my second one story, and the last one I will show you is metastable defects that we found in lithium-rich electrode, which is lithium 2 manganese O3, or we can simply call it LMO. So why do we need the lithium-rich electrolyte, lithium-rich electrode? It is because that we want to have high capacity. But actually there are many problems related to the lithium-rich layer oxide when they use as cathode. The first one is they are unstable. The capacity is lost. It becomes smaller and smaller within the cycling. The second problem is the voltage decay. The voltage is decreased with the cycling. So there are several problems, and those are the big ones. And we want to find out why, and we want to say what's going on if we do the dissociation of the electron. And when we look at the structure of LMO, and we found out if we look at the cations layers, and we have a pure lithium layer, and then we have lithium manganese layer, and then pure lithium layer, lithium manganese layer, lithium layer, lithium manganese layer. Of course, among them there are oxygen layers. And if we look at those layers, the one layer along the same direction is related to each other by a shear vector of 1,6 or 110, which means if we have this layer, one layer shared by this vector, and then we will get to the other layer. From A to B to C, or from A to C1 to C2, there are several possible positions for the layers, for the atoms in the layers to occupy. So this is the sample that we use to do the delization. This is LMO sample, and in the pristine sample, we start to say they are not perfect single crystals. They are actually has different domains. We have 100 domain, we have 110 domain, and also a lot of faulted area with full of defects. And this video shows that the structure changes during the delization. When we take out the lithium out of the structure, and the electron also being taken out from the other side. And now you say there is change not only in the contents of these layers, but also this layers is pristine, is deformed greatly during the delization, especially in the faulted area. Here's a single crystal domain area. This area. The structural evolution is not so big as this in the faulted area. And you see there's a lot of changes here, and especially if we take out the snapshot of the same area, and if we look at it carefully of this high resolution images, and you see here at 0 second, we call it the 0 second as starting point. The stacking of the 0, 0, 1 next plane is A, B, C, 1. And such a stacking sequence became AC2C1 at 301 seconds. And at 408 seconds, it becomes AC2B. So which means that there is a 16 of 110 dislocation gliding. We call it dislocation or gliding through here. So it changes the stacking of the layers of the 0 to 1 layers. So it can identify, and also by using the DFT calculation, such a gliding of the partial dislocation is also related to the lithium extraction. So here the green ones are the lithium ions. And besides the dislocation with the Box vector 16 or 110, we also found a so-called dissociated dislocation with Box vector of half of 001. And you see this video shows the other area of LMO under dissociation. And here's the 001 next plane. And from this video, we can find out is there's a lot of stacking forward, or a lot of defaulted area formed along this direction, which is perpendicular to the 001 next plane. And the density of this fault area becomes larger and larger with the progress of dissociation. And if we take out the image again, if we take out the image and we look at the snapshots that are taken from the previous video, and what we can find is that density of the defects become larger and larger. At the same time, by looking carefully at the enlarged image of these defects, it can be identified as dissociated dislocation, and its Beck's vector is half of 001. And here's a structure model of this dislocation. And then, when we did more experiment, what we can find is this dislocation can not only glide but also climbs, meaning that during the dissociation, the mobility of this dislocation is quite high. And then by using the DFT calculation, what we found out is when we have more and more lithium be extracted from the LMO, the formation energy for the dislocation to form decreased. And once more and more dislocation formed, and then what we found out is the oxygen vacancy formation energy decreased. So from here, what we can say is with the appearance of this dislocation, the oxygen vacancy is easily to form, and then leading to the oxygen loss. So as we can see here, as we illustrated in this image, once we have more and more dislocations with Beck's vector of half of 001, it will promote the formation of oxygen vacancy. At the same time, it will promote the formation of oxygen molecules, leading to the big oxygen release. And once the electrode lost a lot of oxygen, the capacity will be decreased. At the same time, the voltage will be greatly decayed, become a big problem. So this is a mechanism what we found by using the in-situ TM. Now it comes to my conclusion. The first one is the intermediate and thermodynamic undivisible structures which play into role in charge and discharge of battery can be studied by using TM. So TM is a powerful tool to identify those intermediate and thermodynamic unstable structures. And but those intermediate and thermodynamic phases or structures actually are very important to the charge and discharge of batteries. And so the combination of experiment in operon TM data and DFT simulation can provide a new sight into the complex of reaction. And then it can give us more information what happened during the dissociation and solution. That's all my talk. Thank you so much for your attention.